Hello and welcome to the Applied Thermodynamics lecture series. In this lecture, let us continue to study about steam power plant. In this class, we will look at one more method which is used to improve the thermal efficiency in an steam power plant. So that is regeneration. So we're going to look at one more method, that is regeneration method. And based on this method, we are going to take up one numerical problem, which is a combination of a reheat method, which we have discussed in our earlier class, and regeneration method, so which we are going to study about today. So this is what we are going to look at in today's class. Now, if you look at ideal Rankine cycle on a TS plot, we see that we have turbine work which is taking place from state point 3 to state point 4, and we have heat rejection process which is taking place from state point 4 to state point 1, followed by pump work happening from state point 1 to state point 2, and then we have a heat supplied to the working fluid in the boiler from 2 to 3. And we also understood from the previous discussion that in order to bring out any improvement in the thermal efficiencies, the focus has to be on the average temperature at which heat is added to the cycle, or on the average temperature at which heat is rejected from the cycle. So that way, when we consider, we see that the average temperature at which heat is added in the cycle is now depending on from state point 2 to state point 3. Among this, we see that the system is passing through the curve 2 to 2 dash, and then from 2 dash to 3. So when we again look at the sensible heat addition which is happening from state point 2 to state point 2 dash, we see that this is happening at a relatively low temperature, which is not so attractive. So one can bring some changes into the cycle so that we can shorten this process without compromising in the heat addition. So therefore one method has been proposed here, which is called as regeneration method, in which the steam that is getting expanded in the turbine, part of that will be extracted and it will be taken to one device called as a regenerator, and it is also called as feed water heater. Now the steam is brought in direct contact with the condensate, that is also called as a feed water, which is available at state point 1, and the fluid now which is available at state point 1 is called as a feed water or condensate water, will be brought in direct touch with the extracted steam from the turbine, and because of that the average temperature at which heat addition from the boiler will increase. So therefore this magnitude, whatever we have 2 to 2 dash, will be shortened without getting compromise in the heat addition to the cycle. So that way it will reflect in the rise in the thermal efficiency of the cycle. So that is a process of regeneration or a regeneration method. Let us look at the components arrangement. So here we have a components arrangements. This has been discussed now. So we have a turbine, and let's say that 1 kg of steam is being supplied to the turbine, and from 1 kg of steam, some part of the steam after partial expansion is extracted, and that partial extracted steam is now named as M1 kg at section 2, and this is directed to a device called as a regenerator. and whatever is left out from 1 kg will flow and continue to expand in the turbine completely, and then it will pass through the condenser. So what will be left out here will be whatever whenever we deduct this part of the steam which has been extracted from 1 kg, the left out will be 1 minus m1 kg. So this much will be left out. So this amount of steam is now passing through the condenser where heat rejection takes place. So that becomes very clear in the TS plot. From state point 1 we have 1 kg of steam which is flowing partially, which is flowing through the turbine, and from that part of the steam is extracted at state point 2, which is shown here, which is m1 kg. Same thing is been shown on the TS plot. And then the rest of the steam, that is 1 minus m1, will be flowing, continue to expand from section 2 to 3. Section 2 to 3, the rest of the steam will be flowing, expanding. And then we have in the condenser, that is section 3 to 4, section 3 to 4, there is heat rejection happening, considering a quantity of the steam that is 1 minus m1. Then we have from 4 to 5, section 4 to 5 is a pump work. It's a pump work. So 4 to 5 is a isentropic compression process. It's a pump work. And then we see that section 2 meets with section 5 and section 6 at a device, and this device is called as regenerator or feed water heater. So same here we can see that on the TS plot. From section 2, fraction of steam is going to arrive at point number 6, and from point number 5, state point number 5, we have some fraction of steam coming and meeting together at point number 6, and this becomes 1 kg. So when m1 gets added to 1 minus m1, so plus m1 minus m1 will get cancelled, and again it will be back with 1 kg, so as we have earlier. So one can perform an energy balance across the feed water heater in order to find out what is the mass of steam that was extracted after partial expansion in the turbine. And this feed water heater, which is also called regenerator, they are available in 2 types. One is called as open type of feed water heater, the other one is closed type of feed water heater. In case of open type of feed water heater, the steam will get in direct contact with the other part of the working fluid, that is a feed water. So the design of open type of feed water heater is much simpler, and heat transfer characteristics are better. The other type is a closed type of feed water heater, in which the partially expanded steam will going to pass over the feed water inside the device without getting in direct contact. In that way, the steam that is flowing through the feed water heater and the feed water can be at 2 different pressures. The closed type of feed water heaters, they are little complicated in design because of the tubing network, and heat transfer characteristics also are not better compared to that of open type. Now once the fluid, that is a feed water heater from section number 5, gets in direct contact with the steam from section 2, then we are going to get 1 kg of working fluid at section number 6. That same quantity will be pumped at using pump 2 to the boiler at the required pressure. So that is what we see from section 6 to section 7 state points, 6 to 7 state points. So thereby we see very clearly that because of the regeneration, the magnitude of heat addition has now increased compared to that of earlier case where we had a simple Rankine cycle. Therefore we see that now the heat addition in the boiler is 1 H1 minus H7. Earlier it was H1 minus H5 with only one pump by getting rid of feed water heater or regenerator. Now because of the regenerator, we are now able to see that the working fluid is now available at higher temperature with higher pressure. So thereby we see that we have got rid of huge amount of magnitude low quality of heat addition from 5 to 6. So thereby we see that it will reflect in the rise in the thermal efficiency of the plant. Now let us look at the equations. We know thermal efficiency is given as a net work done divided by the heat supplied, and the net work done. Let us now first look at the amount of heat addition. So that happens from H1 minus H7, which is straightforward here for 1 kg. Similarly, the heat rejected, which is happening from section 3 to 4 in the condenser. So that is happening considering a steam of 1 minus M1, not 1 kg, rather it is 1 minus M1. Therefore the heat rejection at the condenser end is H3 minus H4 considering a steam of 1 minus M1. So H3 minus H4 considering a steam of 1 minus M1 in terms of kilojoule per kg basis. Now let us look at the work quantities. We have the work output which is happening in the turbine, and in the turbine we know that steam is partially expanded and it is tapped out at section point 2. Therefore we have 1 kg flowing from section number 1 to 2. So we have H1 minus H2 which is for 1 kg of steam, and then after tapping out a small fraction of mass in order to get directed to the regenerator, then we are left out with 1 minus M1. So that much amount of quantity of steam is now flowing from 2 to 3, from section 2 to 3, the remaining portion of the steam getting expanded. So now we see the second part of the turbine work, that is H2 minus H3, considering a fraction of steam that is 1 minus M1. Similarly, now let us look at the work input from the pumps. So we have 2 pumps here. So one pump is H5 minus H4 considering steam of 1 minus M1 kg. So we have H5 minus H4 considering working fluid that is 1 minus M1 quantity of steam, plus H7 minus H6 for 1 kg. H7 minus H6 for 1 kg. So this is these are the equations pertaining to heat and work. Now let us proceed with the equation for thermal efficiency. We are considering a TS plot as discussed earlier, and then we can have thermal efficiency is equal to the net work output. Please recall that net means we have turbine work and we deduct the pump work from the turbine work. So that case we get net work output. So we have first portion is the partial expansion in the turbine, then the remaining portion of the steam gets expanded in the second stage, and then we deduct that from the pump work. So in the pump work we have H4 minus H5 minus H4 with 1 minus M1, H5 minus H4 with 1 minus M1, plus the work done by pump 2, that is H7 minus H6. This is divided by the heat that is added. The heat that is added in the boiler is H1 minus H7. So the heat input is H1 minus H7. So this ends the thermal efficiency equation for a regeneration cycle. Suppose if we have a reheat process along with regeneration, then what could be the difference? Let us look at a situation where we have a reheat process along with regeneration, and let us now consider some components here representing the cycle, showcasing the reheat process as well as regenerator. So here we have two turbines, and one turbine is called as a high pressure turbine, the next turbine is called as a low pressure turbine. So we have two turbines. Let us now consider 1 kg of steam is being supplied to high pressure turbine, where the steam is going to get expanded and then work will be done by the high pressure turbine, and 1 kg of steam is going to be 1 kg of working fluid is going to be collected at the will be available at the section 2. From 1 kg, some small portion of steam, that is M1 quantity, will be directed to the feed water heater or regenerator, and the remaining portion, that is 1 minus M1, will be now directed to the boiler again for the reheat process. So this is happening at a different pressure. So the pressure at which the working fluid steam was supplied to the high pressure turbine is much higher as compared to the steam which is now available, pressure that is available after the expansion at state point section 2. Then we see that after getting reheated, 1 minus M1 quantity of the steam will be supplied to the directed to the low pressure turbine. So in the low pressure turbine, 1 minus M1 quantity of steam will be completely expanded, and then after extracting the heat energy, the working fluid will go through a condensation process in the condenser from state point 4 to state point 5, section 4 to section 5, and then the condensate, which is also called as a feed water, which is 1 minus M1 quantity, through pump 1 will be directed to feed water heater. And this is the open type of feed water heater, where some portion of steam which was the extracted from the high pressure turbine, some portion that will get in direct contact with the feed water heater. Therefore this is the open type of feed water heater, and this mixes with the feed water from the pump 1, and then 1 kg of working fluid will emerge from the feed water heater at section 7, and using pump 2, 1 kg of working fluid will be directed to pump to boiler once again, where the heat addition will begin, and then again the cycle is going to repeat. So in this case, where we have a reheat process along with regeneration, then one can write the thermal efficiency using this equation, where we have thermal efficiency is equal to work output divided by the heat supplied. Now this is not written as W net because we are now neglecting purposefully the pump work, therefore we don't have net, the word net here. So in that case, we have the thermal efficiency given as turbine work, which is a sum of high pressure turbine work plus low pressure turbine work, which is representing the numerator. So in the high pressure turbine we have H1 minus H2, we have H1 minus H2 for 1 kg of steam, plus, and the turbine work which is happening from section 3 to 4, this is happening with a quantity 1 minus M1, therefore we have for 1 minus M1 quantity of steam, the turbine work is H4 minus H3 minus H4, H3 minus H4, higher enthalpy minus lower enthalpy. So that represents the work output from the turbine divided by the heat supplied. Now again we know that when we have a reheat process here, then heat addition is happening in 2 phases. One is in the regular boiler, that is H1 minus H8 for 1 kg, therefore we have H1 minus H8 for 1 kg, plus the reheat process, the heat supplied due to reheat process, that is the H2 minus H3, H3 minus H2 with the 1 minus m1 kg with 1 minus m1 kg. So we have higher enthalpy minus lower enthalpy, H3 minus H2. So this is an equation for a situation where we have a reheat process along with the regeneration. In the subsequent slides, what we do is we will take up one numerical problem based on the same arrangement of the plant and the components, and we will solve that problem to get a better understanding about the feed water heater or regenerator and a reheat process, along with how much amount of steam being extracted, how to know that. So these things will become a lot more clear to us as we proceed further. Now, based on this understanding, let us now proceed with a numerical problem considering a situation where we have a reheat along with the regeneration process. So here we have a problem which says that in an ideal regenerative reheat cycle, so we have a reheat process and regenerative process, steam enters the high pressure turbine at 80 bar and 500 degrees Celsius, and it expands in the high pressure turbine until it becomes a dry saturated vapor. So if you could recall, on a TS plot we have a saturation dome, and we know that right side part of the saturation dome is called as a dry saturated curve or saturated vapor curve. So it is falling on that point exactly. Then after expanding and reaching to the dry saturated state, some of the steam then goes to an open feed water heater. So we have a regenerator which is open type. Some portion of the steam after expanding from the high pressure turbine flows into the regenerator, and the balance gets reheated to a temperature of 400 degrees Celsius. However, the pressure is not given to us, reheat pressure. We have to work it out. After which it expands completely in the next turbine, that is a low pressure turbine, to a pressure of 0.07 bar. So the remaining portion of the working fluid, that steam, will be expanded completely in the low pressure turbine and to a pressure of 0.07 bar. So this is the condenser pressure. And they asked us to find out the reheat pressure, secondly the fraction of steam that is directed to the open feed water heater, and the last one is the cycle efficiency by neglecting the pump work. So the equation, the problem is well stated. Let us now proceed with the components arrangement showing the reheat process and the regenerator, along with idea about fraction of mass which is directed to the open feed water heater and the remaining working fluid which is passing through the rest of the cycle, and the TS plot. Let us look into those arrangement based on the given problem. So here we have schematic view of the components arrangement, where we have a high pressure turbine, low pressure turbine, 1 kg of steam is being supplied. Among that 1 kg, some portion of steam which we don't know, we are calling it as M1 quantity of steam, which is directed to feed water heater. The rest of the steam will be passing through the reheat process, and then it will be directed to the low pressure turbine. Same quantity of steam will be condensed in the condenser, and through the pump 1 it will be pumped, feed water will be pumped to regenerator. So at the regenerator, the fraction of steam which is tapped out from the high pressure turbine quantity will mix with the feed water at section 6, and 1 kg of working fluid will emerge from the feed water heater or the regenerator, and through using a pump to the feed water will be again pumped to a boiler and the cycle continues. Let us now plot the TS diagram looking into the components arrangement. So we have a TS plot here and we have a saturation dome, and we know that the high pressure turbine is at 80 bar, so we have a pressure curve, constant pressure curve, and the pressure is 80 bar, and this is a boiler pressure P1, we are denoting as P1. And then we have condenser pressure, which is of lower magnitude, having a pressure of 0.07 bar. And then we know that the high pressure turbine does a work by expanding the steam, and the state point 1 is in the superheated region, that we can find it out depending upon the temperature. For state point 1 they have given us pressure is 80 bar and temperature is 500 degrees Celsius. When we look into the data table, we come to know that state point 1 is in the superheated region, therefore point number 1 is existing on the right side of the dome. So we have expansion, and the expansion happens until the expansion steam reaches the dry saturated vapor curve. So it exactly touches the dry saturated vapor curve. That is where we have the reheat pressure curve, which is shown here with the pink curve. So we have a reheat pressure which we don't know, we have to work it out. And we have the next we know that after the expansion in the first turbine, part of that will be directed to the feed water heater, to the regenerator, and the rest will be again reheated, therefore the temperature is rising up. And then in the low pressure turbine the steam will be completely expanded until it reaches to the condenser pressure. So then we have the heat rejection process happening across this curve. Then we have a pump 1, work done by pump work, followed by the work done by pump 2 at this stage from the components arrangement. Now let us number this state point 1 to state point 2. State point 2 is exactly on the saturated vapor curve, and then we can extend this line further because this is an isentropic expansion process. Therefore we can write as S1 is equal to S2. Similarly we have state point 3 to 4. This is an expansion process isentropically happening in low pressure turbine, so we can extend this line until it cuts the x-axis, and we can write as S3 is equal to S4 since it is isentropically expanded in the turbine. Then we have the next process 5 to 6, which is work done by the pump 1 followed by work done by the pump 2, so from 7 to 8. Then at state point 1, when we draw an horizontal line and cuts the y-axis, we get temperature line. Before that, let us look into the mass fraction. We have 1 kg of steam being flowing from section 1 to 2 or state point 1 to 2. Among that, m1 quantity of steam is directed to the feed water heater to the state point 7 or section 7. The remaining will be 1 minus m1, which will be expanded in the low pressure turbine from 3 to 4, and the same quantity of steam, that is 1 minus m1, will be getting condensed and it will reach to the pump 1. Now at state point 1 we can draw an horizontal line and cut the y-axis, and the temperature is given to us in the problem, that is 500 degrees Celsius. Similarly, after the reheat, that is the process from 2 to 3, from the component diagram where it is getting reheated in the boiler. So they have given us at point 3 the temperature is 400 degrees Celsius. Now with this understanding, let us now proceed by finding out the enthalpies at a given state point, that is at state point 1, 2, 3, 4, 5, 6, 7, 8 across the TS plot or across the schematic view of the component plot. Let us now find out the enthalpies so that we can plug into the required equation and get the value of the unknown parameters. So we have now exercise of finding the enthalpies across different state points over the cycle, and we know that we can find out the enthalpies at the state points by knowing the given data. So at state point 1, the given data is a boiler pressure, which is P1 is equal to 80 bar, and they've also given us the temperature of the working fluid, which is at 500 degrees Celsius. So this is a given data. Based on this, they have asked us to find out the enthalpy, that is H1, and also we have to find out the entropy S1. Now to find out the enthalpy, we have to first find out in which phase the system is existing. To know that, we have to refer to the data table and apply the criteria or the guidelines has to be followed based upon the temperature or the pressure. Therefore, let us now look at the data table. So here we have a data table, table number A1, in which we have the list of pressures, and then we have the saturation temperatures in the second column. And they've asked us, and we have state point 1 is existing at 80 bar pressure and at a temperature of 500 degrees Celsius. Therefore, from the pressure column, we are now with 80 bar pressure, and the corresponding saturation temperature here is 294.98. So now when we compare the given temperature, that is 500 degrees Celsius, with the saturation temperature existing at 80 bar, we see that clearly that the given temperature is greater than the saturation temperature, that is 500 degrees Celsius is greater than the 294.98 degrees Celsius. If this is the guideline been satisfied, then we know that the system is existing in superheated vapor region. So one has to refer to superheated tables now to find out the enthalpy at a given state point, that is at P1 and T1. Now let us look at the superheated tables. So we have a superheated tables here, table number A3 and page number 20 as per the prescribed university data table. So we are now with 80 bar pressure. We are with 80 bar pressure and the temperature is 500 degrees Celsius. We are with 80 bar pressure and the temperature is 500 degrees Celsius, and we are looking at enthalpy and entropy. So let us now hold the enthalpy property and then move along the horizontal line, and we see that the enthalpy at a pressure of 80 bar and at a temperature of 500 degrees Celsius, it is 3398.8 kilojoule per kg, and the corresponding entropy at 80 bar and 500 degrees Celsius is 6.7262 kilojoule per kg Kelvin. So with this we got directly the values for H1 and S1. Suppose if the temperature was like 550, then one may have to go ahead with interpolation, but here there is no need for interpolation because we have values directly available at 500 degrees Celsius. So now let us proceed with the rest of the problem. So we have now found out from the data table what is H1 and what is S1. So we have H1 and S1 from the data table we have picked up. Now let us now look at state point 2. Let us look at a TS plot. At state point 1 we have now worked out what is the H1 and S1, and we know that S1 is equal to S2. That means at state point 2 we know the entropy, and now we also know that this is state point 2 is exactly lying on the saturated vapor curve, that is dry saturated condition. Therefore, the procedure here is we have to hold the given entropy value, that is S1 is equal to S2, and through the steam tables we have to go on searching for SG value, where exactly the S2 value will coincide with the SG value. So the point where these two resembles, that is a point where we are going to find out the corresponding intermittent pressure, which is called as a reheat pressure. So now let us refer to the data table. So in the data table we have table number A1 here, and the first column we have pressures, and in the last column we have SG value, that is entropy at dry saturated condition. We know that since the state point 1 and 2 it is an isentropic expansion process, therefore S1 is equal to S2, and the value was 6.726 kilojoule per kg Kelvin. So this value has to be close to that of SG value from the table. So from the table, looking at SG value, let us go on targeting this given value for us. So we are now looking for 6.72 or 6.75 in other words. Let us now proceed further, move one by one along this last column, and we see that it is 6.8. It's not matching with our required entropy value. We'll proceed with 6.75, which is closer to this value. We go to the next value, that is 6.70, which is again lesser than this value, which means that the given state point is lying between these two entropy values, that is between 6.70 and between 6.70 and 6.75. So therefore one has to interpolate this, and so that on the pressure column we can find out what is the exact reheat pressure. But for the present problem I am considering 6.75 as the SG value, which is closer to this of 6.72 for the simplicity purpose, and along this line we find that the corresponding pressure is 6 bar. So this becomes the reheat pressure, and the corresponding enthalpy will be HG value. So we see that 2755.5 kilojoule per kg will be the H2 value at state point 2. Now let us proceed with the problem, and we found that S2 is closer to that of SG, and 6.75 being a value that we were looking for, and at that point we found that HG was representing to us the H2 value, and the corresponding pressure we called it as intermittent pressure, that is the reheat pressure, was 6 bar. So this fulfills part of the question being asked. They asked us to find out the reheat pressure. So with this procedure we arrived at reheat pressure, that is 6 bar in this present problem. Now let us proceed with the state point 3, and we know that from process 2 to 3 is a reheat process where heat is getting added. That's why we see that there is a rise in the temperature along the y-axis, and we know the pressure now because this is a constant pressure curve. Everywhere the pressure is 6 bar, and at state point 3 they have given us a temperature that is 400 degrees Celsius. Therefore we have now 6 bar pressure and temperature of 400 degrees Celsius. Now let us look into the data tables and see where exactly this state is lying. So we have a data table here. So we have a 6 bar pressure, and the corresponding temperature within the bracket is shown to us. This is the saturation temperature. But when we look into the given data, we had a reheat pressure as 6 bar, and the corresponding temperature was 400 degrees Celsius at state point 3. But here when we look into the value in the bracket, which is showing us the saturation temperature, so the saturation temperature is 158, which clearly shows that the given temperature, that is 400 degrees Celsius, is greater than that of saturation temperature, at 6 bar pressure. So this clearly shows us that the system is lying in superheated region. Therefore we are now referring to the superheated table, and that table is A3 and page number 18. Therefore at 6 bar we are referring to 400 degrees Celsius. So 400 degrees Celsius is given to us here. Along this column, when we come down to the required cell, then we find that we have looking for enthalpy and entropy. So when we look into the horizontal line, then we come across enthalpy value at 400 degrees Celsius, that is 3270.6 kilojoule per kg. So this becomes our H3 value, and the corresponding entropy will be the S3 value, corresponding entropy. So with this we have worked out our state 3. So at stage 3 it's a superheated table, so we refer to superheated tables and we traced the values of H3 and S3. Now let's proceed with state point 4. Please recall that state point 3 and state point 4 it is isentropic expansion happening in the low pressure turbine. Therefore we wrote as S3 is equal to S4. So whatever we obtained, the value for S3 is also valid for S4, because S3 is equal to S4 from this plot, TS plot. So we have at state point 4 they have given us the condenser pressure, that is 0.07 bar, and we know that the state point 3 to state point 4 was isentropic expansion process. Therefore S3 is equal to S4, which is 7.7090 kilojoule per kg Kelvin. Now the procedure here is we have to find out whether the system is lying inside the dome or outside the dome. That means the state point 4 from the TS plot, is it inside the dome or is it outside the dome? That depends upon the SG value at the corresponding pressures. The pressure here is 0.07 bar. At 0.07 bar, from the data table, when we look at SG value and compare that with S3 is equal to S4 value, if the S3 value or S4 value is less than SG value at 0.07 bar, then the system is lying inside the dome. Then we have to apply the concept which is applicable for the system lying inside the dome and find out the enthalpy. If the given entropy value, that is S3 or S4, if it is greater than the SG value at a condenser pressure, that is 0.07 bar, then it is existing in the superheated zone. We have to refer to the superheated tables. Now let us proceed with that process. So here we have table number A1, and the first column we have pressure, and from the problem at state point 4 we have a condenser pressure, that is 0.07 bar, and S3 is equal to S4, and our target value here is 7.7090 kilojoule per kg Kelvin entropy value, and we are now looking at a pressure of 0.07 bar, and we are now looking at SG value, and we are compare with the given entropy value. So we see that as we proceed column wise downward, we come across at 0.07 bar, the SG value is 8.2767 kilojoule per kg Kelvin, but our given entropy value, that is S3 is equal to S4, was 7.70, which clearly shows that SG value is greater than S4. That means the given SG value is greater than the S4. That means the state point 4 is lying inside the dome, Therefore the system is existing in two-phase mixture region. Therefore if the system is lying in two-phase mixture region, then we can apply the equation for enthalpy as H4 is equal to HF plus X4 into HFG, and from this table we know that HF value is given to us 163.4. we can plug into that, and using entropy equation we can find the dryness fraction x4. We can substitute that into this equation, and then HFG value from the HFG column we can trace out, that is 2409.2, plug in and get the value of H4. So that is a process we are now going to follow now. So we found that it was a mixture region, therefore since the state was inside the dome at state point 4, we are applying a equation S4 is equal to SF plus X4 into SFG, and S3 is equal to S4, therefore we have the ready-made value here, that is 7.7090 is equal to SF value from the data tables at 0.07 bar, we note it down, plus X4 is unknown, dryness fraction we don't know, this is also called as quality, and SFG value from a pressure of 0.07 bar, we substitute that, and the only unknown here is X4. Rearrange this equation and get the value of X4 as 92.64%. This value we are now going to substitute in the enthalpy equation. So we have enthalpy equation at state point 4 is equal to H4 is equal to HF plus X4 into HFG, and from the data table at 0.07 bar we note down HF and HFG value also likewise we note it down as 2409.2, and we got the value of quality as 92.64%, therefore 0.9264 we have substituted here, and working out this equation we get H4 value as 2395.28 kilojoule per kg. So we are now done with finding out the enthalpy at state point 4. Now let us proceed. We have now so far worked out 4 enthalpy values across the different state points at state point 1, 2, 3, 4. Now we are remaining with H5, H6, H7 and H8. Now we know that H5 is exactly on the saturated liquid point, and we know the corresponding pressure which is existing at this point, condenser pressure, that is 0.07 bar. So referring to the tables, we can find that at 0.07 bar, 0.07 far, and for HF value when we look we see that the HF value is 163.4 kilojoule per kg. So we note this value. Therefore HF at 0.07 bar is 163.4 kilojoule per kg. So with this we are done with finding H5, and H6 we'll now find out H6. We apply an equation that is dH is equal to V into dP. Therefore we have an equation dH is equal to V into dP, where we have H6 minus H5. H6 minus H5 is equal to specific volume at state point 5 at 0.07 bar existing, and these two are the curves. One curve is the reheat pressure curve, the other curve is the condenser pressure. Therefore we have the pressure difference existing between the reheat pressure and the condenser pressure. So we are going to take H5 to other side of the equation, and we straightforward substitute the values from the data table at 0.07 bar, and VF at state point 5 we get this value from the data table into the reheat pressure, which is 6 bar. We have substituted that in terms of kilopascal as 600 kilopascal, and pressure as 0.07 bar, which we have substituted in terms of kilopascal as 7 kilopascal. So working out this equation we are going to land up with a value of H6 is equal to 163.99 kilojoule per kg. So with this we have completed the enthalpy at state point 6. Now let us look at enthalpy at state point 7. Again state point 7, this point state point 7 is existing at a reheat pressure that is 6 bar, and it is on a saturated liquid point. Therefore HF value will give us directly at 6 bar the enthalpy for H7. So we have 670 kilojoule per kg. Now again, to find out the enthalpy at state point 8, we are going to apply the equation, that is dH is equal to V into dP. So we have dH is equal to V into dP, taking minus H7 to the other side of the equation. At a pressure of 6 bar, we are going to look at HF value and VF value at 7 bar, at 6 bar, and the pressure difference is now existing between 0.7 and 0.8 is the boiler pressure and the reheat pressure. Therefore we have boiler pressure minus the reheat pressure. In terms of kilopascal, it has been substituted in order to get the answer in kilojoule per kg. So rearranging the equation and substituting the values at a pressure of 6 bar, we are going to arrive at value 678.54 kilojoule per kg for enthalpy at state point 8. So friends, with this we have worked out all the enthalpies across the cycle at a different state points. So now let us summarize all these enthalpies. Let us put them together in one single chart. So we get all the enthalpies which we worked out now from H1 to H8 and the corresponding entropy values. Since state point 1 and 2 were isentropic process, so these two values are similar, and process 3 to 4 was isentropic. Once again, these values are similar. Now before proceeding, we have to find out what is the fraction of steam that was directed to regenerator. To find out that, we have to take up energy balance across feed water heater. So now let us look at the component schematic view. So we are now at feed water heater. So we see that section 2 is getting connected to feed water heater and section 6 is connected to feed water heater, and the addition of section 2 and section 6 will give out section number 7. So we are going to perform energy balance across this feed water heater. So whatever the enthalpy that is available with M1, we are going to call it as H2 because this is at section 2, therefore H2 into M1, and whatever the enthalpy that is available at section 6 is called as H6, and the mass of steam that is available here is 1 minus M1. Therefore we can write it as 1 minus M1 multiplied by H6. So that will be available at the inlet of feed water heater, and the addition of these two quantities of steam along with the enthalpies will give us H7. So that is what we are going to do now. So we are going to take up an energy balance across the feed water heater as I briefed 1 minute ago. So we have mass of steam, that is M1 quantity, coming along with the enthalpy of H2 that is at section number 2, that is from this point, and we have enthalpy H6 coming along with the quantity of steam that is 1 minus M1 across section 6, that is from section 6, and these two quantities, they are meeting at point number 7. That means they are going to mix up in the open feed water heater, and the sum of these two quantities will be equal to H7. So the sum of M1 and 1 minus M1 along with the enthalpies will lead to H7. So when we do that small exercise, so we have M1 into H2, that is M1 into H2 coming in, plus H6 into M1 1 minus M1, that is 1 minus M1 into H2 should be equal to H7, so this is an energy balance equation. Therefore let us now take H6 into the brackets. Then we simplify that. We are going to get a common term here as H2 minus H6. Take out the M1 outside. Therefore M1 will be equal to H7 minus H6 divided by H2 minus H6. 7 minus H6 divided by H2 minus H6. And we know that we just worked out all the enthalpies, so we have the list of enthalpies which are readily available to us. H7 is 670.4 and H6 is 163.9 divided by H2 is 2755.5 minus H6 is 163.9. Once we plug in all these enthalpy equations values into this equation and simplify that, we are going to arrive at 0.2 kg. So that is a mass of steam that was extracted from high pressure turbine and it was directed to regenerator, that is feed water heater. So we are now comfortable finding out the M1 quantity of steam by carrying out the energy balance. Now proceeding further, we are now left out with the last parameter, that is a cycle efficiency, and they told us to neglect the pump work. So we have the equation now, that is output work divided by heat supplied. So based upon the TS plot, the work output is the sum of the work which is happening from the turbine 1 and the turbine 2. Turbine 1 is H1 minus H2 from the TS plot for 1 kg of steam, and the portion of remaining steam after directing the steam to the regenerator, what is left out will be 1 minus M1. For this 1 minus M1, the rest of the steam will be expanded from section 3 to 4, therefore we have H3 minus H4. That will be divided by the heat supplied in the boiler, that is H1 minus H8, plus rest of the steam heat which is supplied in the reheat process for a quantity of steam, that is for 1 minus M1 into the change in enthalpy, that is H3 minus H2. Now again we have the list of enthalpies here. We have H1, we have H2, we have H3, H4. We can plug into the numerator quantities, and then in the denominator we have H1 and H8, plus we have M1 also, that is 0.2 kg here. We can plug in those, and H3 and H2. Once we substitute those quantities into this equation and simplify and work out, we are going to land up with 42.6% the thermal efficiency for the given cycle. And please recall that for a simple Rankine cycle, the efficiency is somewhere, we obtained somewhere around 30%, and with the modifications on the simple Rankine cycle in terms of reheat method or in terms of regeneration method, we can always see that percentage is now rising. And this is a problem where we had a combination of reheat along with regeneration, and we see the rise in the thermal efficiency, clearly showing that the improvement or the modification that was done onto the system is reflecting in higher thermal efficiencies. So friends, with this we have come to the end of today's lecture. We encourage students to refer to the following textbooks for more understanding on these methods. Thank you for your attention.